right. Welcome everyone to Science in Action for Fall 2020 semester. Really would like to thank you guys for taking your time to visit with us. But Science in Action is a weekly Tuesday event, 4:30 to 5:30, right at this Zoom call. And we have it available at our STEM Center website for access to all the Zoom links for future Science in Action events. But we also do record these and upload them onto our YouTube channel for future viewing at a later date. But wanted again to thank you guys all for being here. I'm Brian. Welcome to our second Science in Action of Fall 2020 semester. I'm really excited to kind of talk to you guys, share some time with y'all to talk about some of my research that I did in my undergrad experience after I transferred. It was at Occidental College. And so the title of my talk is going to be From Dirty Logbooks to Dirty Data, the Impact of Benfords Law. Okay, so let's go ahead and get right into it. So wanted to again welcome you guys with a nice puppy before we kind of dive into the mathematics here. Start nice and sweet. Just a quick agenda to share with you guys. I'm going to start off with my educational journey, where I went, what classes I took, why did I end up choosing math as a major, and then I'm going to dive into my comprehensive research project that I did during my time at Occidental College. We called it COMPS for short, and my focus was specifically in Benfords Law, which is the topic of conversation today. In that conversation, we're going to be starting off with a demonstration, provide some historical context, and then I'm going to dive into my research work and my experience with that, and then ultimately kind of ask or address the question of why. Why is this important? Why am I wanting to talk about this with you guys at this time? And so let's just get right into it. And so starting off with my education, much like yourselves, I was a community college student. I didn't get to go to Skyline College. I did get to go to Lake Tahoe Community College. And I was there for about 3 years, from 2008 to 2011, straight out of high school. And during my time there, I was very much kind of this academic explorer. I didn't really know what I wanted to do as a major during my 3-year time there. And so listing off some of those majors that I did declare. At one point, I was a psychology major. I dabbled in business. I was a biology major, tried chemistry, physiology, philosophy, computer science. And so a lot of these courses were relatively STEM-centric. And so when I met with a counselor, we were able to put those classes together and apply for an AA degree in the natural sciences. And this whole time, markedly so, I was never a math major during this period. It was only until when I was filling out transfer applications did I commit to being a math major. And why was that exactly? Well, a lot of it kind of had to do with the fact that my parents had a lot of influence or a lot of persuasion in some of these career choices that I had, right? And so for my parents specifically, some of you guys may be familiar with it, but they were really pushing the big three. So doctor, lawyer, and businessman, which left me with a kind of conundrum because on the onset, when I take my declared majors during that phase, I felt like there were kind of these unique and distinct trajectories, right? If I wanted to be a doctor, I at the time felt like I had to be a biology major or a chemistry major as a prerequisite for med school. Contrast that with wanting to pursue a law degree, right? I felt like I had to declare a philosophy or a poli-sci major, but then definitely not biochem or business. Likewise, if I wanted to be a businessman, I wanted to declare in the business major and kind of stay away from the other disciplines.
So right. Brian, Professor Hainwork is asking no physics?
Unfortunately, no. I was very intimidated. So y'all are brave, braver than I am for taking physics. Yeah, sorry. But, it was interesting because like for me, I was so scared of picking a major or picking a career, and it would pigeonhole me into a certain trajectory that if I had, changed my mind a couple years down the road, it would have been a significant, restart. I had to start from the ground up again, and I was essentially scared of commitment. And so remarkably, in this context, this is where my choice of becoming a math major came into play, because math as a degree allowed me to keep all three of those options open. I just didn't want to disappoint my parents, but at the same time, I didn't want to commit to something that I was too scared to committing to. So it was my fear of commitment. Right. And so the justification here is that math kept all of my options open because simply it was quote unquote rigorous enough to keep my resume competitive, yet it was ambiguous enough to apply to a number of different professions. And so with this mindset, I transferred to Occidental College, and I was there from 2011 to 2013 for 2 years. And during my time there, I was able to achieve a Bachelor of Arts in Mathematics with a minor in computer science. And listing off some of these math courses that I took once I transferred to Occidental was discrete math, numerical analysis, differential equations. I also took real analysis, probability theory, number theory, computability and complexity, Java, data structures algorithms. And finally, I had to complete a senior research project in Benfords Law, which was delving in statistical theory. But it was a very unique shift in tone that I felt from my community college math experience with my university math experience, or Occidental College math experience. At Lake Tahoe Community College, I felt like my math courses was this sequence in which what allowed me to climb a certain mountain, right? One foot after another, kind of continuously building up to this kind of apex math course, I guess, where everything kind of mattered in the previous course as I carried it on to the next course. Now, at Occidental, I felt like that kind of sequencing was completely absent. In fact, I felt total freedom to kind of run around in math and kind of dabble in a bunch of different things, a lot of different perspectives, a lot of different approaches, and none of these classes necessarily served as a direct prerequisite. It's not like I needed to know real analysis to have any kind of understanding of number theory and vice versa, right? And it really kind of it led to a certain realization that, simply put, the spirit of math is just problem solving, right? All we do, and kind of looking at the math history of things, right? All it is that we're fueled with curiosity, and we simply attempt to answer questions that we're just thinking about, that we're pondering. And sometimes you just have to make stuff up along the way, notations, methods, approaches, perspectives. And that's the part that makes it challenging, right? Is that as we're kind of looking at solving certain questions, we had to develop our own toolbox to kind of answer them or address them, or even better, understand them. And so it makes it hard and almost inaccessible, because a lot of the times we're building stuff up for our own benefit without necessarily any consideration for the other, right? And that's kind of where the challenge is born, but also where the beauty kind of comes from, right? And this field that I was prancing around in can be best demonstrated by this map of mathematics that I pulled off of the internet. And so, what we can see here is that there's no sequencing whatsoever. Nothing kind of necessarily comes before the other. Each of these unique disciplines allow us to kind of tackle or understand specific types of problems that arise, that we question, right? So although maybe I may not have taken physics precisely, but mathematical physics is part of that this map. as it's a unique perspective that allows us to understand physics better, right? Which is uniquely different from, say, set theory, which is far off and to the left, right? Each of these have a unique approach or a unique methodology that allows to tackle certain questions that we're curious about. And so if I return back to my education and the courses that I took, and if I wanted to kind of organize this in a particular way and how it fits into the map of that mathematics, right, it breaks down like this. The discrete math was a prerequisite course. I took a few applied mathematics courses, some more theoretical mathematics courses, and then a handful of courses that allowed me to finish my minor in computer science. And so all of this kind of culminated in my research project in Benfords Law, which is also not a class that I took, but it was heavily steeped in statistical theory. And so we're going to kind of transition from my educational experience or background and kind of now zero it in and focus in on this concept of Benfords Law, which was my research topic. Okay, and so Benfords Law. It describes a phenomenon that one finds when looking at a real life sets of numerical data, right? Quantitative data, in other words, quantitative data that occurs or is observed naturally. And better yet, we only need to look at the first digits of these expansions of this numerical data set, okay? So looking at the first digit, right? It's so consistent that it has been applied in criminal court cases to prove fraud in numerical data, right? And so in the above points, right, we're talking about some observations or phenomenon that we're seeing of what we should expect to see in our data that exists naturally. Any kind of deviation from this is a justification for us to argue that this data isn't natural, okay? Now, it could be unnatural due to a bunch of different factors, right? It could be due to just a clerical error, a significant human event like the coronavirus going on right now is having a huge impact on how all of our numbers kind of play out, right? But the more sadistic, the one that I'm more fearful is this case of fraud. And in fact, when we're talking about how consistent it is, in the past, in a legal court system, it does hold legal precedence in order to prove guilt, okay? And so it's much like matching a fingerprint in a crime scene. We're not saying that if you have a matching fingerprint at a murder scene, right, it's not guaranteeing that this is the killer, but you better bring significant evidence to the contrary to unpackage that association. And so, you know, what is this Benford's Law exactly? And let's actually look at a demonstration. So in that theme of fraud, what I did was I took a screen cap of just a template tax form off of Google Images. Now, if I was a forensics accountant, right, what I would be most concerned with is all the numbers in this data set. But not just those numbers in that data set, but those first digits. Now, if I took those first digits and I organized them in a sort of histogram or a bar graph, what kind of shape of these, what kind of shape of distribution would I expect to see, right? Now, one possible candidate would be that it's a close to uniform distribution, right? And in context, right? If we have 9 digits available for us, there shouldn't be any bias, right? There should be an even distribution of all of our numbers starting with a 1, 2, 3, all the way up until 9. The alternative is that there is a bias, right? Where there's a heavy bias towards leading digits of 1, 2, and a 3, and not so much of the later digits, like numbers starting with a 7, 8, or a 9. Right? If this is one type of bias, why not consider another type of bias? Something that fits more of a bell curve, right? This is kind of ubiquitous. You see it a lot and everywhere. Might as well see it here. And so I want to take a second to kind of just get audience feedback, right? I felt very strongly of what I should expect to see when I first heard about this, but I want to hear your guys' input real quick. So real quickly, if you guys can do me a favor, all of you participants, just go ahead and turn on the annotation feature and go ahead and like mark up, circle the distribution that you should expect to see when we plot the first digit frequencies. And so I'll wait a second. Yeah.
Andre is asking, how is this practical?
How is this practical? That's a great
and it's coming, right?
yeah, it's a great comment, and I hope to address it later on in the slide, but if I don't do it justice, definitely make sure to ask me at the end and I can maybe provide some more context here, but I don't want to do a spoiler alert for later on. So if you guys wouldn't mind turning on the annotation feature, go ahead and just circle X up the distribution that you guys would expect to see when we start plotting a histogram of the first digits. Okay.
How do we turn on the annotation feature on this?
Yeah, so up in the top center of your viewing screen.
I uploaded a picture.
Oh, okay.
With it. So if you can find the picture that says annotate, you can see where it is there.
Okay, when I hit download, nothing opens up.
Oh, okay, sorry about that. So it's on the right-hand corner, up right-hand corner. It's a tiny label that says annotate, and there's a caret. You press it.
I don't have that on mine.
No worries. Go ahead and type it in the chat if you'd like. Send it to a direct message to me, right? But we're seeing quite a few responses here. We have a handful of A's, a lot of B's are coming up, and a couple check marks at C and a circle, a star. Beautiful. Thank you guys for that. Now, without further ado, I am going to.
So Karamoko said it's they. He thinks it's they.
Okay.
Or she's got it.
Beautiful, beautiful. All right, so I'm going to turn off the annotation on my end here, close that out. All right, so drum roll. It's actually B. And when I first heard this, I distinctly remember when I first heard this phenomenon, it was actually a podcast on Radiolab. I was actually driving down from Sacramento, where my parents were at, driving down to Los Angeles, where Occidental was, and I was just marathoning Radiolab podcasts, and this topic came up. And they're like, yep, not a uniform distribution for first digit frequencies. And I nearly crashed my car because I was so shook. No way that this is true. Like, I couldn't believe it. And it took me a while to convince myself that this was actually, in fact, true. And before we kind of dive into the Benford's Law analysis in a more mathematical perspective, I wanted to provide a bit more of an intuitive justification. Now, I want you guys to kind of imagine a tree, right? 1 foot tall. Now, in terms of going from 1 foot height to 2 feet tall, what we have to experience is about 100% growth to go from 1 foot to 2 feet. Now, going from 2 to 3 feet, we're no longer experiencing 100% growth, right? Because an additional foot is only 50% of a 2 foot length. And so we're experiencing 50% growth from 2 feet to 3 feet. And again, 3 feet to 4 feet, we're looking at a decreasing proportion of 33%. And finally, last but not least, we're looking at a 25% growth from 4 feet to 5 feet. And so this sequential decline of percentages of growth kind of lends itself to the intuitive justification as to why Benford's Law holds true, right? And I want to kind of cycle back to kind of having seen this justification. I want to go back a little bit and kind of examine Benford's Law's history. Like, where did this even start? Where did this even come from? And it all starts with, ironically, Simon Newcomb. Simon Newcomb was an astronomer or a mathematician, and he did a lot of work in a more astronomy sense. He was in the 1880s, 1879, around that time. He was really focusing his work on establishing the speed of light, trying to measure that through a series of experiments. Okay, and he was collaborating with a fellow astronomer by the last name Michelson, who designed these experiments to try to calculate how quickly light moves in the late 1800s. And in that process, his calculation involved the use of log tables. Okay, and log tables, a brief math review here, is recall the logarithm property of if I take the log of x times y, it's the same evaluation as taking the log of x and the log of y and adding them together. Now, this is a drastically more efficient way to multiply very large numbers together, right? So late 1800s, we're talking about a time where we were doing a lot of these massive calculations without any use of a calculator. And how did they handle that, right? Well, they could do it by hand, right? Now, hypothetically speaking, a demonstration as to how addition is way faster than multiplication, right, is if we did it by hand, you know, looking at a 9-digit number added to a 9-digit number, the operations here are pretty straightforward, right? You add the 9 to the 1, 8 to the 2, 7 to the 3, all the way down. And so really, we're adding numbers together up to 9 to 10 times, considering carrying numbers, okay? Now flip that to a multiplication. Now in a multiplication problem, right, way back when in grade school, we were told, okay, start with the 1, multiply to the 9, the 8, the 7, the 6, the 5, the 4, all the way down. And then not only that, we have to do that with all 9 other numbers. That's 81 operations to multiply a 9-digit number to a 9-digit number, okay? That's a lot. And we don't got time for that. That's just too much time. And so the use of log tables was a very quick and efficient way, right? Take that 9-digit number, look up its log value, right? And take the other value, look up its log value, and add those two together, and then use the log table again to reverse engineer the original number. And that was the efficient way of calculating these numbers, especially when we're talking about the velocity of light, right? Something that has a huge quantity. And so in this discovery, right, when Simon Newcomb was doing these calculations, trying to establish the velocity of light, he noticed something with the log table, that the front half of the book was way dirtier than the back half of the book. And to him, that just meant that I'm using these values closer to the front of the book way more than these values that I'm looking up towards the back of the book, which led to a thought that the 10 digits do not occur with equal frequency. And turns out that was the beginning of his paper. And this is the first paper documenting the phenomenon that's now known as Benfords Law. And it's the paper titled Note on the Frequency of the Use of Different Digits in Natural Numbers. And literally his thought was the first line of this paper, okay? Now, he laid the ground foundation. Now, fast forward, you know, a few decades to Frank Benford. Now we're getting to the guy this law is named after, even though Simon Newcomb was the one who discovered it. And in his work around 1937, 1938, he added to Simon Newcomb's work by saying, like, yeah, there is a bias towards the leading digits of a 1, 2, or 3 rather than a 7, 8, or 9. And what he did, or what he contributed to this analysis, is that he started pulling all sorts of data from all different sources and started looking at their first digits, right? And so this is a table from his paper, The Law of Anomalous Numbers, where he started looking at all kinds of data points here, right? Some including rivers in their areas, population sizes, infamous mathematical constants, right? The list goes on. And he kind of took a very deep dive and started compiling all of these digits, or compiling all these numbers, looking at their first digits and counting their frequencies. And he noticed that it's remarkably fitting the same distribution that Newcomb observed, which led to his equation that would describe the expected frequency of each leading digit, right? And that was kind of his result, his contribution to the work. And I wanted to add this other figure into the presentation because it was also in his paper. But in this table on the right, you're seeing the theoretical frequencies mapped against the observed frequency of footnotes in 10 books, each having at least one page with 10 footnotes. Like, this guy was extra, but he did a full comprehensive analysis of all these data points and looked at their first digits. And he noticed this is a remarkably consistent phenomenon.
Question, Brian.
Yeah.
Jocelyn asks, can this law be applied to small and large sets of data?
Yeah, that's a really good question. So Benford's Law applies under certain specified conditions. It just fits more closely the larger your data set is. But based on the intuitive explanation, the behavior you can already start seeing with relatively small data sets. But in the claim or proof of Benford's Law, the more numbers you have, the more significant this phenomenon is. That's a great question, thank you. And so fast forward from 1937 all the way up until 1995, it was left at this, whoa, this is a really cool fact, until 1995. Theodore Hill, who was a mathematician, finally was able to prove and statistically derive that this is in fact a true behavior of naturally arising numbers, numbers that you would find in the real world on their own, okay? And in this kind of attempt, I wanna go back to the previous slide, that the spirit of math is problem solving, but sometimes you just have to make stuff up along the way. And the things that Ted Hill had to make up to get to this point was the topic of my research. And so I wanted to kind of dive into this real quickly, right? Is that the first thing that I had to look at in terms of understanding how the heck Ted Hill was able to accomplish this fact was that he started with this notion of a sigma algebra, which is a very common topic that's being taught in a typical modern algebra course once offered at the upper division level of mathematics. Sometimes you'll see it in your physics class as well, okay? But as a definition, what we would do is define a capital A, defined as a non-empty set or a collection of items. And that this capital sigma, capital Greek letter sigma, be a collection of the subsets of this non-empty set A. Now, we can call capital sigma a lowercase sigma algebra when we have the following conditions hold. The first is that cap sigma is non-empty. Cap sigma is closed under complementation. And cap sigma is closed under countable unions. Now, this is a lot of heavy jargon, but essentially this is a tool that allows us, so sigma algebras is a way or a mechanism that allows us to consider specified measures, allowing us to quantify their sizes or relations. And so like in the context of a statistics class, we study a thing called a sample space and probability. A sigma algebra is the sample space is an example of said sigma algebra.
You want to take a question now, Brian?
Sure, sure.
So Karamoko wants to know how you can detect if the regression model is fraud or not true.
I think I'll get to it towards the end, but again, hold on to that question. And I just don't want to do a spoiler for the end there. All right. So we talked about a sigma algebra as a notion of defining a a sample set that allows us to calculate certain probabilities. Okay. Now, we needed to take that concept and now amend it so that we're allowed to quote unquote sample the real numbers. And this is done by a topic called the burel sigma algebra for the positive reals, R+. Okay. Now, what this is saying is that the burel sigma algebra is generated by intervals of the form interval A to B, where 0 is less than A is less than B. This opens up the discussion of probability measures associated with intervals of positive real numbers. In essence, we're now defining the elements of our sample space to be intervals of positive real numbers. Now, a burel sigma algebra not only in this realm holds significant value, but it's also heavily explored in topics like measure theory, which focuses on formalizing or generalizing concepts of length, area, volume. It's like the theory of measurability, okay? It's also used in topology, which is the study of geometric properties and spatial relations. And so bringing it back to the map of mathematics, we're really looking at these sections of said map. Now, let me remind you, we started our analysis on the opposite side and denoted in that red circle, right? And somehow we're kind of cherry picking these topics from measure theory and topology and applying it to the notion of statistics because this is the tools that allows us to make this investigation. And so Ted Hill took that concept and was like, well, this isn't good enough. I need a better form. And so now we're dealing with a mantissa sigma algebra, denoted by this capital M. And so here we're dealing with a sub sigma algebra of the burel sigma algebra for R+. Say that 5 times fast. I don't think I can. And now by definition, every set in M has representation of this form down here. Okay, now this is some heavy notation, but in essence, what we're really trying to look at here is those intervals that you see on the number line in red below. The first interval, 1.1 to 1.4. The second interval, 11 to 14. The third interval, 110 to 140. In a mantissa sigma algebra, we're allowed to classify all of these things as the same. And now this is great for us because this allows the analysis to be focused on those first digit frequencies, right? Mantissa sigma algebra, this is a lot of heavy jargon. I want you guys to think about scientific notation in this context here. I want to use Avogadro's number as an example, right? We would define, like we call the mantissa the decimal expansion part in this scientific notation. And so Ted Hill was able to kind of co-construct this concept that allows us to focus in on the mantissa and not focus in on the magnitude, right? To the 10 to the power. With that, we can now start assigning measures or probability associated with these objects, right? And so this was his definition from Ted Hill's paper. And so, you know, the structure of probability measure mu sub sigma on R plus B, together with the probability space sigma FP constitutes the random probability measure M. Breaking it down just slightly, mu sub sigma denotes the set of burel probability measures, while the occurrence of omega determines the selection of probability measures. And then this is just kind of an operation that allows us to assign values based on the elements that we identify in our sample space, which is the mantissa. And so, you know, again, basically a random probability measure mimics the way Benford sampled from all these types of data sets, and that this mantissa sigma algebra mimics Benford's focus on these leading digits when identifying these problems or this phenomenon. Okay, and so when Ted Hill managed to formally reconstruct Benford's process, he was able to examine the properties of a sigma algebra, a burel sigma algebra, a mantissa sigma algebra, and kind of inherently reconstruct very key properties that exist within the real number system. Okay, and in particular, what he kind of created here is this theorem called the log limit law for significant digits. And so based on these constructions, he was able to kind of ascertain certain very key properties. The fact that M is scale unbiased and M is base unbiased. What that's really telling us is that whether or not we measure the area of a lake in square feet, which is base 12, or square meters, which is base 10, we're still guaranteed to observe the same phenomenon, okay? Which is really, really crucial here. We can't just cherry pick the fact that Benford's Law suits base 10 numbers, right? It has to be kind of more ubiquitous. And we don't intentionally look for this property, but based on the characteristics of real numbers and these sigma algebras, we actually get it for free. And so he was able to kind of show all of these properties were interconnected, and really the phenomenon of Benford's Law can be captured in the 6th point here. For every M random K samples, we get this logarithmic distribution for these first digits, okay? And so that was kind of my experience in my senior year of Occidental College, to kind of take this very technical paper that was a first attempt at trying to prove something, and really just breaking apart the pieces of just his definitions. And so where does this leave us, right? Like, Ted Hill managed to prove that this property holds for all positive real numbers. And it left us with quite a bit of impact in my perspective. And I've learned a lot of lessons from this process. First, feed your intellectual curiosities. It may lead to unintended yet useful intellectual leverage, I like to call it, right? It's really interesting that this phenomenon here started off with a guy going, yo, there's a dirty book, but just the front half. Why? And now we're getting it used in a situation where in the early 2000s, that era where the market crashed, Benford's Law had a role to play in the Enron scandal. And a lot of these fraud case scandals, Benford's Law played a role in that, right? What was an unintended consequence? It's not like Benford was looking at a logbook going, I want to prove fraud in taxes. But eventually through this analysis, we get this very effective tool to kind of verify whether or not data is authentic or natural or not. And I think that's really crazy. Another lesson I learned is that first attempts are messy, complicated, and heavily unorganized. It's hard, but it gets easier over time or as one gets used to it. Okay. Now, Ted Hill was able to kind of conquer the formalization of how Benford's Law actually works or applies, right? But over time, we were able to kind of come up with easier, nicer explanations, right? Going back to the tree example, right? That's an adequate justification. But in order for us to pinpoint for certain in a mathematical sense, that first attempt required the very technical, very jargon-heavy approaches, right? And my last kind of lesson learned here is always, always, always ask questions, all right? And this kind of broadens to all of us as students here. You know, we're always kind of engaging, you know, in school, and a lot of it is focused in around your guys' learning and what you guys know and what you guys don't know. Only you guys have the answers for those. And, you know, us as instructors, we're here to kind of help provide that. But, you know, we want to be able to help guide based on kind of like the curiosity or kind of where you guys or where students stand. And so, you know, and kind of like my experience, you know, asking questions is a great way to kind of engage and understand. But it was also this like weird realization that I had through my research process. Like, I didn't know what the heck was going on with that paper when I was first coming across that concept or the topic. I just was shook that it wasn't a uniform distribution. And I was just like, but why? Right. And it was weird for me because there was these moments where like people were asking me like, Bryan, how do you do it? How are you studying math? How are you like researching this stuff? And you know what? It took me a second where like, holy crap, I'm actually doing this. It was really funny to me because I never thought I was actually actively doing math research. It wasn't until I was asked that question where I was like, oh shoot, I am a mathematician. I am investigating this stuff. You know, like a lot of these times we're kind of like thinking I'm about to do mathematics and or whatever, what have you, right? It doesn't have to be mathematics. And it's like, how do you do it? How do you start? It's like, just start and ask questions. And eventually over time, you may not find yourself doing it, but then all of a sudden you're getting kind of the people that you work with, the people around you, you're like, you're doing it. And I'm just like, I was just cluelessly like bumping around from professor to professor the whole time. And so I kind of bring it back to the point of like, always, always, always ask questions. And that will start any kind of research process. And all it takes is asking questions and just a willingness to engage and an understanding that the first time is gonna be messy and complicated. And so I kind of want to end it there and give plenty of time for questions at the very end. So yeah, thank you guys for your attention.
From Professor Khan, big capital letters, truth, Brian. Or should I say Brian?
Yeah.
So one of the questions, Brian, that we get back to, how can you detect if the regression model is fraud or not true?
Yeah.
From Karamoko.
Yeah. That's a really good question. So I'm kind of, doubling back to the whole fraud thing. Whether or not it follows Benford's Law or it violates Benford's Law, it won't 100% determine fraud. Again, like Benford's Law is an observation of what we should expect to see of natural numbers. And so, you know, if the data set is not fitting Benford's Law, all we can say is that this is not natural. And so if we're talking about kind of establishing proof that fraud does exist, Benford's Law isn't enough. But at the very least, it gives us the safeguard of at least understanding whether it's natural or not. And I want to kind of tie it into what's going on right now, right? We're about entering phase 3 of trials for the vaccine coming out to kind of fight the coronavirus, right? COVID-19. I'm thankful that we have Benford's Law, because at least when the data comes out on the efficacy of these COVID vaccines, I want to make damn certain that this is a natural result as opposed to a result that was cooked up for the sake of PR. I'm not saying that the data that comes out from, you know, like if it violates Benford's Law, that this is not authentic or this is not an effective vaccine, right? But at least it gives us some agency to call bullshit when we see non-natural data sets. And so I don't want to say that this is our golden key to proving fraud, but it does have this legal precedence that allows us to use it as evidence to question the naturalness of our data. Does that answer? Just want to make sure.
Yeah, that answers my question. I was typing in another question in here, and it's kind of crazy. I was going to ask you, can we apply that to multiple choice questions, for example? So let's say you have a multiple choice question on a test, and it's A, B, C, and D. Now, do we use that probability scale to look at A and say, hey, A is probably 31 point, let's say 7% of the time accurate, and then apply B, C, D as 2, 3, and 4 on our scale to identify certain probabilities of answering certain questions on exams?
A little game theory attempt here with multiple choice questions. Unfortunately,
we applied this Benford's theory to that.
Unfortunately, no. And the reason why comes from the fact that multiple choice is not a natural thing that we're kind of cooking up, or it's not a natural thing, period, right? Like whoever's writing the test or the multiple choice questions.
Well, let me rephrase that. Let's say, for instance, you have door 1, door 2, door 3,
Mm-hmm.
right?
Mm-hmm.
Can you use Benford's Law against that? So let's say you're playing on a game show and you got 3 doors, and let's say the contestant eliminates one of the door. That changes your probability. So
Right.
could we use Benford's scale for that to identify which is more probable? So like if you had door 1, 2, and 3, your odds to get the reward is 33% in each door. But if you eliminate one door, your probability is now 66% for door number 1, or 66% for door number 2, and still 33% for door number 1. So your probability changes based on your number. Can you use this theory to calculate for that?
So I think you're referring to the Monty Hall problem, which I'd be happy to talk about. But the Monty Hall problem was a funny situation because it was a game show for real. It was from Let's Make a Deal, and the Monty Hall problem explains a very counterintuitive strategy that you're actually mentioning, where you can double your probability of winning the car. That was the scenario in the Monty Hall problem. Again, I kind of go back to the point that these numbers have to be natural, right? The doors and the selection process, that's entirely human,
well,
right?
Because that as a fraud base.
Right.
So that door is a fraud base because everything has to start with number 1 for the natural number, and your number 1 should be rated at your highest percentage, and then your percentages should drop. So I'm using that term as, can you identify fraud using the other theory based against the Benfords theory?
Yeah, that's a good question. So I'm going to go back to this slide here.
Remember when you said you couldn't calculate for fraud, right? But we're thinking in probability and percentages, correct? When we're doing these numbers. So if the number doesn't line up and the percentages change going from 1 to 9, and they double somewhere down the road, isn't that a way to check for fraud?
But we're still missing the part that the numbers, the data has to be pulled from a natural observation. So I'm going back to this tree example because technically with this tree is going to grow whether or not I do anything to it or not, right? Like barring chopping it, right? This tree's going to grow. And when it's in that growth process, we're experiencing this decline of proportion in which it has to grow to change the leading significant digit. And so what you're introducing as these kind of distinct door values, there's no growth or there's no kind of naturalness that's kind of involved here. So unfortunately, this won't be a situation that Benford's Law applies because of that influence, right? One necessary condition is that we have to have these numbers being pulled from real life data.
Okay. All right.
Another question from Amy, Brian. If I'm not a math major, can I still apply these in any area of my life as a student?
Benford's Law specifically, if you're dealing with natural data sets, yeah, right? You should expect to see, right? If you're kind of pulling number measurements off of the real world based off of observations, right? The first digit frequencies should follow. I'm not saying that it's guaranteed to follow, but it should. And it's remarkably consistent in that manner. But necessarily, will I be using Benford's Law like throughout? If you're a forensics accountant, yeah, sure, why not? You know, but however, like I think the more ubiquitous aspect of this whole process is the nature of inquiry, and the fact of just kind of this perseverance to kind of dig deep and use what you have at your disposal while simultaneously kind of understanding that it's a messy process, that's going to take a while, and asking questions. Those are like the things that is fairly universal, right, in any kind of field. So will you use Benford's Law specifically? I hope so. But I'm not going to say we're going to have to know it or you're going to have to use it. Yeah.
It could apply as things get older, like ourselves. So we can apply it there as we get old. A comment from Lucy.
Banking and stuff like that, like cost analysis projects and stuff like that. You could apply it to that, like banking and stuff. Yeah,
yeah, absolutely.
So a comment from Lucy. I joined late and don't think I saw enough to ask questions, but it's super cool to hear about your work. Thank you for this. I'll have to watch the recording later.
Yeah, I'll edit it tonight and then I'll upload it later this evening, hopefully. So it should be live by tomorrow afternoon.
And also, if you have questions later on after the event is over, feel free to come back to us asking questions. But still, we are there in Discord.
Yeah, absolutely. I'm happy to talk about any of this anytime. Monty Hall problem is one of my favorite topics as well, because it's been like, its history as well is really interesting, because it was a real game show. And so people who knew of this statistical phenomenon took full advantage of doubling their opportunity of getting a brand new car. So
yeah, because the percentages change. That's what I was talking about, like your percentages. A lot of people don't know that. Now you go from, it's still not like split at 100. It's like one door is still at 33%. Now the other door is doubled to 66%. And then you can base your calculations off of that.
Man, I should have changed my topic. It should have been the Monty Hall problem. That's a fun one.
So, no worries.
Brian, would you mind typing your email address on the chat?
Yeah, sure, absolutely.
In case someone wants to come back with questions.
Yeah, I'll go ahead and stop screen share, and then I'm going to go ahead and add a couple of links here. But yeah, absolutely. Feel free to check in anytime you'd like. I went ahead and added my email into the chat. And also, I am very frequently on our STEM Center Discord server. And I want to make sure that I include an invite link if you guys haven't joined already. But while I do that, is there any other questions that anyone may have that I can help answer?
I got my last one. I wonder how you can tie them into one another.
They're related based on the notion of probability. Unfortunately, like with Benford's Law, we're actually dealing with like continuous numbers where decimal expansions are a thing. And the Monty Hall problem involves more discrete values, like whole number values only, right? There's no such thing as door 1.5 or anything like that. So they're tied based on the notion of establishing probability measures, but outside of that, we're kind of dealing with like completely different sampling processes or where we're pulling from.
Got it. Okay.
But so it's about 5:30. So I'm going to go ahead and stop the recording, but we're going to go ahead and keep this Zoom call open for anyone who may have any last questions.